So today I will talk about efficient detection of non-classicality of continuous variable states using uh, moments of Wigner function. I will describe the terms from basic, the term non-classicality, continuous variables, and also the moments of Wigner function. And this is a brief outline of my talk. In the introduction, I will talk some mathematical preliminaries and motivation why we need to do this kind of work. Then I will go to our work where I will talk about Wigner moments and our detection criteria. Then I will propose something experimental kind of stuff that we can do with already proposed stuff in literature. And I will conclude with a brief summary, and then question and answer will follow. So till now, many people has already talked about continuous variables. So in quantum information theory, we can broadly divide it in two categories. In discrete variables, we talk about qubits, spin degrees of freedom, so on, where the degree of freedom is finite. And in continuous variable, we talk about situations where we have continuous eigenspectra, for example, position, momentum, or the vibrational degree of freedom, and so on. And this situation can be described using the infinite dimensional Hilbert space, and that can be described using the Fock basis. They are just the eigenstates of the quantum harmonic oscillator. And as a prototype, we can use the quantum harmonic oscillator. For example, in classical situation, if we have a well-behaved oscillation, we can break it down in Fourier analysis into sinusoidal terms, which are just the solutions of the classical harmonic oscillator, and they're represented by their specific frequencies. In quantum situation, we can use this kind of Hamiltonian, where we add up the Hamiltonian for the quantum harmonic oscillator, and each term is represented by the creation and annihilation operators. They tells us the mode of that specific term. And we can go to quadratures using this kind of transformation. Here, x and p are just the position and momentum quadratures. And with those position momentum quadratures, we can go to a different kind of representation called the phase space representations. There are many. I will talk about only Wigner representation. Now, the Wigner function is just mapped from the density operator to a function. This way we can go from rho to WXP, and this is a one-to-one map. That means if we know one, we can go to the other. Now, since W is a function, we cannot use the operators in quantum theory directly. We need to use a map that takes the operator to the function, and that is given by this Weil transform. And we can see that Wigner function is also a map that takes the density operator to Wigner function. And here the first few Wigner function for the Fock states n equal to 0, 2, 3 are plotted. And in Wigner picture, we can get the exact expectation value of some operator or the observable using this kind of equation that somehow looks similar to what we do in classical physics. Now, there is a big question from very early years of quantum physics, that where is the exact boundary between classical and quantum physics? And to answer that, if you look at classical experiments, we take suppose we're doing an experiment, we take the data for quite a large number of trials, and then we take the average values, and then it becomes just the observable times the probability that outcome came, and then we take the sum. And for continuous outcomes, instead of discrete probabilities, we take the probability distribution and the observable as a function of the variables. Then we take the integration, and then we get the expectation value. But in quantum mechanics, if we try to use the same equation, we see that there is some differences there. The probability distribution function goes to the Wigner function. And the main difference is that the Wigner function can take negative values. So it's not a probability distribution anymore. So there we get a boundary. If W is positive, then it's exactly a probability distribution, then it's classical. And if it can take negative values, if it takes negative values, then there is no classical counterpart. W is then called a quasi-probability distribution. And in my talk, non-classicality basically means the presence of negativity in the Wigner function. Now, people can ask that, well, there is some differences. This is quasi-probability, but why it is important to detect the Wigner negativity? The main reason is that there was one result by Mary and Isaac, that is the generalization of Gauss-Mann-Neal theorem from quantum computation. And they showed that if we use a Wigner positive function and do operation that preserves the Wigner positivity, then whatever we do, whatever be the entangled measure of that state, we can do everything using a classical computer. So what is the need for a quantum computer? So it becomes a necessity to use Wigner negative states in quantum computation. And there is also follow-up works like quantum computational speedup. And also it has been shown that if there is Wigner negativity, then it gives us advantages in various information processing tasks. And recently it has been shown that Wigner negativity and contextuality, they are actually equivalent. Now, to detect Wigner function, the Wigner negativity, we introduce the concept of Wigner moments. And this is a very simple concept. We take the nth power of the Wigner function, then we integrate over all the quadratures. And whatever be the number of modes, here we have written in 2 modes, but that is not necessary. Now, then we start our mathematical stuff. We start from Wigner positive function, then you use the LP space and use the Cauchy source inequality kind of thing. And after a lot of mathematical stuff, we get to this condition, omega 2 square less equal to omega 3. And that is a necessary condition for Wigner positive function. Now, when a necessary condition is violated, we know that we get a sufficient condition for the opposite result. So if this criteria is violated, we sufficiently get, or we can comment that the state must possess Wigner negativity. Now, for example, if we talk about Fock states, the ground state is a Gaussian state and it is positive, we know, and it is shown by our criteria that it does not violate our criteria. And all other Fock states from n equal to 1 to any n greater than equal to 1, they violate our criteria. And we can see that from the plot as well. The ground state, the plot with A, that is Gaussian, and the states with n equal to 1, 2, 3, they are non-Gaussian and also Wigner negative. And we can see that they have negative regions. And for the second example, we can consider the known states where we have n photons in a mode and there is 0 photon in the other mode. It's a 2-mode state. And with this state, we can calculate the Wigner function and then we can check whether they violate our criteria or not. And we found that for all n greater or equal to 1, they violate our criteria, hence they are Wigner negative. Now, if we compare with other known methods to detect Wigner negativity, for example, witnessing Wigner negativity, they are state dependent. Or the other way, we can do tomography to get the Wigner function in direct way or indirect way. In the direct method, we construct the Wigner function directly. In the indirect method, we first construct the density operator, then we do Fourier transform to get the Wigner function. But the advantage in our scheme is that we need to calculate only simple functionals. We need to calculate only some integrations to know whether there is Wigner negativity or not. And the second advantage is that, so for doing tomography, the number of states and the measurements required are exponential. But since we are not trying to know the Wigner function exactly, we're just trying to know whether there is Wigner negativity or not, we need very less number of copies. That's polynomial in the number of mode of the system. And finally, our method is state independent. So no prior knowledge is needed about the state. So that is some advantage over the witness stuff. Now, the experimental proposal. So it has been recently proposed, the continuous variable swap operator by Volkov in 2022. And that looks like this way? Well, they represented it using the using the creation and annihilation operators, but it can be written using the quadratures. Now, how it operates, it just swaps the creation operator from mode 1 to mode 2, and the action is clearly written here. Now, to use the swap operator in the Wigner function formulation, we need to use the while form of that operator, and that is given by this expression. And this is not the exact expression. We need to do the integration, then we get the form of the while form, then we can use it using the Wigner formulation.
Sudip, 2 more minutes.
Okay, okay. Now, in the experiment, what it has already been proposed for to detect the partially transposed moments, and there uh, it was proposed by Johnny Gray, Shogoto Bose et al. In 2018. Now, to realize the second order moment, we need two copies of the state. So the tensor product over two that represent that we need two copies. Then we can use the while form the swap operator, and this gives us directly the second order moment. And it's been shown that the swap operator is experimentally realizable by Volkov. And for the third order moment, we can use the permutation operator of order 3 that is represented by FP3. But the advantage is that this permutation operator can also be written using swap operators. The order, the sequence has to be accurate. For example, we are talking about two mode situations. So there are, and also we are using three copies. So there is Alice 1, Alice 2, and Alice 3. Then there is Bob 1, Bob 2, Bob 3. Now in the Alice part, if the swaps are done in this order, Alice 1, Alice 2, then Alice 2, Alice 3, then Alice 3, Alice 1. Now in the Bob's part, it has to be done in the opposite situation, that is Bob 3, Bob 2, then Bob 2, Bob 1, then Bob 1, Bob 3. And if we follow the sequence, then we can readily write that FP3 using the swap operators, and we can realize the third order moment in experiments. So since we can realize the moments W2 and W3 in experiment, we can actually detect our criteria, and we can comment whether the state is Wigner negative or not, and whether should we use it for quantum information processing task or quantum computation or not. And that requires very less number of measurements. So in conclusion, we have introduced the concept of moments of Wigner function, and we have also proposed the criteria how can we detect the non-classicality, that is here Wigner negativity, using those moments of Wigner function. Then we have given some examples, some in the talk, and some more examples are there in the paper. And finally, we have shown how we can experimentally realize the moments using the continuous variable swap operator, and that establishes our protocol's experimental feasibility. Thank you.
Okay, thank you, Sudip. Now there is the question session, and in the question session, there is the first question from Asis. Asis, please, you may ask.
Thank you, sir. So to get the Wigner moments, we need the Wigner distribution. So again, to get the Wigner distribution, we need the quadrature data. So and for that, is there and again it comes back that you need to either perform get the quadrature data, do an inverse data transform, or do the tomography, get your density matrix, and then do Fourier transform.
No. Actually, in the experimental kind of thing, experimental proposal, we showed that we need two copies, but we don't need to know the Wigner function. We can actually cite that part. We don't need to know the state or the Wigner function. We will just know the moments. So in mathematical proof, we used all the data, but that is true mathematically. But experimentally, we don't need. We did the mathematical stuff just to get to the criteria.
So experimentally, let's say we are in the case of a experiment, what are the things that we need to measure here? Like quadrature data, but for like, is there a way in which you can reduce the number of measurements to just get the moments, or is that the correct
actually, you are not doing the quadrature measurement here. So the swap operator, there you don't require the quadrature measurements. You can look at that Volkov paper. Actually, it's experimental one, but there you can see that you are not actually measuring the quadratures.
Okay,
Okay,
thank
sir,
you,
thank you.
thank you, Sudip. You may connect, Ashish. You may connect with Sudip directly. Second question is from Professor Sur. Yes, Chiranjeev Sur, and please, Chiranjeev, you may ask directly to the
Yeah.
Sudip.
Hi. So the relation that you had with two moments, so basically it's a relation between the second and third moment, right? And it's a sufficient relation for Wigner negativity. But now, I mean, your approach, what it seems like, I mean, you can basically do any moment that you like. You can do eighth moment as well if you have 8 copies of the
Yeah.
system.
I can
So now
detect any
instead
moment.
of only, I mean, relation between two and the moment 2 and moment 3, you can have like a progressive chain of inequalities with higher moments, which bounds the
We
system
are
even more.
trying to do that.
So
Actually, this is our
can you
next
do
work.
like a complete detection with that? Yeah. Okay.
Yeah,
Okay.
we are doing that. That is the work I'm doing right now. That
Mhm.
for example, if we are talking about mixed states, then though our criteria is sufficient, but that is not that good. Many states which are Wigner negative, our criteria cannot catch them. But
So
when
this
we
sequence of
increase the moments, then it is the
Mhm.
simplest one with
So
third
the
order
sequence
moments.
of moments that we have,
Yeah.
I mean, apart from this, so is this sequence finite, or do we have an infinite sequence of moment relations to actually, I mean,
No, we don't
ideally
need to go to
bound the
infinite.
complete thing?
We don't need to go to infinite sequence. So actually, we can get the optimal criteria using finite number of moments.
Oh, amazing. Thank you. Great talk.
Thank you, Chiranjeev.
Hello.
Thank you, Sudip, for
Yeah.
the nice talk. Now,
Hello.
Oh, it seems
Yeah.
there is another question.
Thank you so much for the talk. I have one question. This might be a stupid-like question. I'm not very much familiar with this function. So my question is that if the function gives exactly 0 values, then what does it signify? It is something like quantum interference, or this cannot be concluded anything.
Well, if there is a zero outcome, then we actually cannot comment about Wigner negativity. Because for Wigner negativity, violation is required, and that is not less equal. That is exactly has to be positive. That is greater than 0. Then we can comment.
Okay, so then for this case, we just can't conclude anything else, right?
We cannot conclude anything.
Okay. Thank you so much.